How's everyone doing? This will be an installment of a mini lecture specifically about hybridization and the concept of hybridization of atomic orbitals and building upon what we've learned about bonding and getting a little more complex. So currently we have studied the bonding of small atoms and different amounts of bonding on linear molecules and then molecules with a central atom with anywhere from 1 to 6 different bonds or 6 different electron domains. And essentially what we have shown in the case of a very simple molecule such as hydrogen is that once the two electron clouds, or the two electrons, one for each hydrogen, get close enough to one another, they can overlap to some degree, and the minimization of that energy because of a proton in the nucleus, that minimization of energy because we have now made protons and electrons interact with one another at a distance that is favorable energetically, we create a single bond, right? And up until this point, we have shown this in a Lewis structure to look something like that, right? That's what's occurring here. Now, this formation of that single bond, as we've currently been studying it, is the overlapping of the electrons in the 1s orbital. Remember, hydrogen is in the first period. It only has 1s orbitals. However, this is a simplistic and truly oversimplified for the purposes of what chemists continue to study, because a lot of people disagreed on this as the true nature of the chemical bond. Now, notice that these two electron clouds are coming at one another head on. And because they're spherical, obviously that overlap would be the edge of one sphere with the edge of the other sphere. This overlap, for purposes of atomic orbital hybridization, is going to be known as a sigma bond. Sigma being this lowercase symbol here. This is a lowercase Greek symbol, sigma. So we will call these sigma bonds from here on out. Now let's talk a little bit about what the hybridization theory. Now, if we take a look at these two images, we should be familiar with the s orbital, spherical, obviously centered at the origin, and we see a z, x, and y axis. And then our p orbitals, which are doubly, have two lobes with a node at the center at the origin, and we have one that centers the x, the y, and the z axes, right? And I've tried to draw these somewhat three-dimensional to show you for reference. Obviously, we have px, py, and pz. And where I show the dotted line, that's going into the plane of the paper, obviously. And the others are in the plane or coming out of the plane of the paper. Now, what we found is that based upon the number of electron domains, which we've seen and studied already when we talk about Lewis structures, hybridization can be predicted. But what's actually happening? Now, for purposes of this class, what's actually happening is a little beyond the scope. But imagine if each one of these particular orbitals, p or s, has a wave function, which we've kind of already talked about. That wave function represents some mathematical function of the probability density, where we can find these electrons. Imagine if we were to kind of merge them, and that's why they call it hybridization, because we will be merging these electron densities, mathematically merging them in three-dimensional space, and we will create new, what we call hybridized orbitals. And these are the three hybridized orbitals that we will be focused on. However, there are more, but we would focus on these three, and that would be sp3, sp2, and sp. Notice that each letter shows us what orbitals have been merged together, and the value at the top tells us how many of each of them have been merged. So in the case of sp3, notice we have utilized one s and three p orbitals, and there are only one s and three p orbitals, so that is 4 total orbitals being hybridized, and that will give us 4 hybrid orbitals, as we'll see. And the same goes for each of the others, and we're going to show examples of each of these and molecules for each of these as well. But the reason that we did this is because we see that this actually describes the three-dimensional geometry that we've already studied. It describes it better. Okay, what do I mean? So let's take a look here. This is an sp3 hybridized orbital. Notice that these orbitals are little skinny, similar to the p orbital. Notice they're not necessarily symmetric in their lobes, but there are 2 lobes, and notice that I have shown this down here. That is what an individual sp3 hybridized orbital looks like, but we have 4 of them. Why do we have 4? Well, we merged 3 p's and 1 s, but I'm showing you the picture of one. Notice that there's a little small like bulb on the bottom. It almost looks like an exclamation point, right? Cartoon exclamation point. If we put all of those with the node being here at the origin, we would actually get this same flower tetrahedral shape that we're familiar with in our three-dimensional Lewis structures, but these are describing the areas where we are likely to find any of the electrons associated with that atom's electron structure. So how do we fit 4 electron domains around a given central point? Well, the best way to do that is tetrahedrally, and we're familiar with that, 109.5. So for example, we could take carbon, which has an electronic configuration that I've shown you here, 1s2, 2s2, 2p2. And we can take those orbitals of s and p in the second period, those 4 electrons that exist in those orbitals, and merge those together to create 4 hybridized orbitals to create sp3, and we see that we essentially have 4 electrons spread out over all of this entire image here. And you can think of them as little dots, but remember they are also waves. So if we spread those 4 electrons out, then it makes a little bit more sense how bonding does and what would be better described for, let's say, a molecule such as methane. So imagine if each one of these blue sphericals are hydrogen, bringing in its 1 electron, and each one of these purple lobes are the sp3 hybridized, bringing in 1 electron each from our carbon atom. We could actually create that single bond that we are familiar with in the case of methane that we've been showing like this. And again, everyone should be familiar with being able to draw your three-dimensional Lewis structures. But electronically, this is a better description using the sp3 hybridization, but we achieve the same thing, 109.5 bond angle, and we also achieve orbital overlap, and that orbital overlap that exists right here, this is the sigma bond that we spoke of, right? That is a head-on overlap of both electron domains or electron densities of both hydrogen and carbon to create an electron domain, which we have shown as a single bond. So this would be 4 sigma bonds to create methane using sp3 hybridization. So you need to be able to answer for a given question in the upcoming exams. What kind of hybridization, how many, and what type of bonds are being created. Okay, so this, just give you a quick look. sp3 hybridization is 4 lobes hybridized by 4 separate orbitals. Those 4 orbitals are the 3p orbitals, x, y, and z, and the 1s orbital. In the case of methane, this would be the second period, so 2s and 2p, and then we find what the molecule looks like from a hybridization standpoint. And being comfortable drawing this would benefit you greatly, right? So let's talk a little bit about sp2. So what happens when there are only 3 electron domains around a central atom where bonding is occurring? Okay. And what would that look like? Well, if we look at sp2, we are taking 2p orbitals and 1s orbital, which would give us a total of 3 hybridized orbitals, or 3 lobes. These lobes would be very similarly shaped, as we saw before. It's kind of a exclamation point. And these lobes would be placed at the center point of the origin. The nodes would all overlap at that center point. And when we have 3 bonding or electron domains around a central atom, right, 3 electron domains, we end up with trigonal planar geometry. That is the best way to space them away from one another at 120 degrees. Now, we must also not forget that we did not use all of the orbitals. We only used 2 of the p orbitals, and in this case, I chose to represent this by a leftover py orbital in the py axis. Hopefully this is clear. My 3-dimensional drawings aren't that great, but the leftover p orbital in the py axis, that is shown here in red. Okay. Now, that leftover py axis can be involved in bonding, and we will show some of that in later content, later videos, and I'll talk about that in class. But for purposes of, let's say, use the example of boron, which can be an exception to the octet. Boron carries 3 valence electrons in the 2s and the 2p, shown here. And what happens if we were to merge the 2s, 2px, 2pz orbitals together to create sp2? Again, sp2, 3 lobes, 3 orbitals being merged. And we would then have 3 electrons spread out over this volume, right? 3 electrons. So essentially, we have an electron potentially residing in each one of these lobes, right? Now let's talk about a molecule with this same structure. Boron trihydride, from a Lewis structure perspective, is shown like this. Again, this is being used as an example. Recognize this is an exception to the octet rule. Remember, we talked earlier that boron is an exception to the octet. It is also trigonal planar geometry. We know that because it has 3 electron domains and 3 bonding domains. And if we were to use hydrogen once again as the bonding, we end up with that 1 electron in hydrogen bonding and overlapping with the 1 electron that potentially resides in the sp2 hybridized orbital. So here we have the hybridization and the type of bonding occurring. Notice this is head-to-head bonding, and we would expect this to be sigma bonding. And in this case, the creation of 3 sigma bonds is what would give us boron trihydride. The reason that this is better shown, okay, using hybridization is because we know from mathematical modeling and experimental studies that these bond angles are 120. But if we just left the bonding of boron trihydride up to p orbitals, then they would be 90 degrees. And maybe you'll see that if you take a look at your p orbital orientations, notice that they are not 120 degrees from one another. Let's go back real quick. Notice that each of these bond angles here that we are familiar with are 90 degrees. So something must have changed, okay, for us to be able to get the molecular geometry that we know exists for boron trihydride. And this is where the orbital hybridization theory helps us, or what we call valence bond theory. Last but not least is sp. So sp hybridization, shown here, will only have two lobes. One s and one p orbital will hybridize together to create two electron domains, or two hybridized orbitals. And remember, whenever two electron domains, or domains with negative charge, are interacting or around a central atom, we expect that angle to be 180, meaning that we expect this to be linear, as we can see here in the drawn diagram. So I chose to use the z-axis. So we merge the 2s spherical orbital with the 2pz, creating sp hybridization, and this is linear. So another exception to the octet rule, and also an exception to the metallic bonding rule that we've learned, but this is good for the purposes of this particular example. Beryllium can actually form semi-covalent bonds, or bonds that we would describe as covalent, and because of its position in the periodic table and it only having two valence electrons, we actually find that beryllium can hybridize the 2s and the 2p in that second period, because it is a second period element, and those two electrons can actually form covalent bonds with sp hybridization. And yes, it forms them with hydrogen. So the hydrogen 1s, or that one electron, can potentially overlap and create bonding head on with the sp hybridization, and we end up with, yep, you guessed it, another sigma bond. The py and px in this case are left over. We do not have to worry about them interacting in this particular molecule, but we will see in future molecules that these can and will interact when we have to deal with double and triply bonded molecules, okay? Double and triply bonded molecules. So we need to be able to utilize the Lewis structure, in this case, the Lewis structure of beryllium dihydride would look like this. We should be able to recognize that there are only two bonding or electron domains around beryllium, which will give us 180 degrees. So we should expect this to be linear from a molecular geometry standpoint, but we have to transition from just strictly knowing our molecular geometry into being able to recognize what we expect that to look like. So let's talk a little bit about an example that is not one of these three, and we'll finish here. What about our friend oxygen? So we're familiar with oxygen as a central atom, specifically with water. Fairly straightforward molecule. At this point, we should be able to draw it. We should be able to recognize that it has lone pairs and bonding domains. But because there are generally 4 domains around oxygen in water, we would expect it to create sp3 hybridization, right? Oxygen, basic Lewis structure drawn like such. And because there are 4 electron domains around oxygen, we should expect hybridization to be able to accommodate all of them. Okay, that's the key. Can your hybridization accommodate all of the electron domains? But in this case, we have seen, or we should be able to see, that some of these domains are going to be involving a single electron that is utilized for bonding to the hydrogen, and some of these domains are going to be utilizing these pairs of electrons that we already know exist on oxygen as a central atom. So for purposes of drawing this and being very clear in how this is drawn, we should be able to recognize that the head-on sigma bonds that we're familiar with at this point are existing where the hydrogen overlaps the sp3 hybridized orbitals of oxygen, and those are the single bonds that we're familiar with. Now, if we drew this utilizing our wedges and dashes, we should recognize that the hydrogen will be coming out of the page, the other hydrogen will be into the page, and the lone pairs I have left in the plane of the page, if you will. Okay. And this is bent molecular geometry, right? But the hybridized orbitals still have tetrahedral geometry, and we would expect that this bond angle be less than 109.5 due to, well, this bond angle, I apologize, will be greater than 109.5, but this bond angle would be less than 109.5, right? Because the lone pairs repel more than the bonding domains, right? And we recognize that from our VSPER experiment in the laboratory. So there are sp3, sp2, sp, and then an extra sp3 example showing that even when lone pairs exist on the central atom, we can still utilize valence bond theory to predict orientation, molecular geometry, and to predict these bond angles. And this is a more specific and more it gives us a better idea of bonding, more so than just strictly drawing these Lewis structures. It gives some explanation to where these bond angles can naturally come from. So look forward to some more videos on this topic. If you have any questions, feel free to email me. And this has been another mini lecture with Professor Bryant.